Okay, hello everyone and welcome to Aspirin Revision. Okay, so in the current video, all I'm going to do is go through the essential information that you need to know for the SAC, as well as a practical application of that. So answering some past exam questions. Now, all of the exam questions I'm going to be talking about are currently on Dropbox, and they are under Unit 3 and Practice SACs, SAC 3, and then it is actually called Video for Aspirin SAC, and it's in a PowerPoint, and it's got all the answers as well. So first of all, things that you must know for the aspirin SAC. So what I would suggest is you know both reaction pathways to produce aspirin, as well as which one is preferred for the synthesis of aspirin. So we learned about that in class, and basically I'm not going to go through it in any great detail, but you must know the structure of salicylic acid, which looks like so, and then that we can react it with either ethanoic anhydride. You need to know what that looks like. And here is an anhydride because ethanoic anhydride was produced from two ethanoic acid molecules, like so, via a condensation reaction. So that's why pretty much it's called an anhydride, because it was produced via a condensation reaction, like so. And then therefore the products of this reaction are aspirin, acetylsalicylic acid, which I'll draw out. You should be fairly comfortable with the structure of aspirin, okay, and the fact that it is less soluble than salicylic acid. So this is more soluble because it's got 2 points of hydrogen bonding, whereas this is less soluble because it's only got 1 point of hydrogen bonding. And then the other product is ethanoic acid. Whoops, OH. This is the preferred pathway. It is faster, it has a greater yield, etc. The other pathway, which we add ethanoic acid, produces aspirin, but also water, so it's less preferred. And it's slower and it has a lower yield. Okay, now possible errors in the experiment. So a couple of you rattled off some errors. So loss of transfer by mass, loss of mass by transfer, things like that. I'm sure you can think of more, but also thinking about the effect that these errors will have on yield. Okay, states of reactants and products. So we're going to go through that in a minute. But basically, salicylic acid, you know, was a solid, and ethanoic anhydride was pure, so it was a liquid. Aspirin produced was a solid, and then ethanoic acid was a liquid, pure. And you might notice a vinegar smell at the bottom of your flask if you take a smell. Information in chapters 9 and 10, I said, is examinable. So functional groups, knowing ester, hydroxyl, carboxyl, amine, amide, all of those functional groups in that table, as well as naming and reaction pathway. That's all assumed knowledge because a lot of that information underpins the assessment of aspirin. You also have to know how to determine atom economy. So atom economy pretty much is very easy. It's looking at economically how much of our reactants are going into producing our products. It equals the molar mass of product of interest divided by molar mass of all reactants times 100. You'll notice that the atom economy of this pathway, the preferred pathway, is actually lower than the one that produces water because water doesn't weigh much. Okay, also knowing how to calculate percentage yield, also knowing that salicylic acid, so we know that salicylic acid looks like so, Here we've got salicylic acid. Okay, it might react at 2 points via an esterification reaction. It might react at its carboxyl group, and in that case, we would need an alcohol to react with it via a condensation reaction. It might react at its hydroxyl, and it would need to react with a carboxylic acid. So here we would have producing. So each of them are producing an ester. In this case, if we add methanol plus salicylic acid, we would get methyl salicylate. And salicylate, make sure I do not get the incorrect spelling for that. So we would get methyl salicylate. Excellent. And then obviously if we have ethanoic acid and the aspirin and salicylic acid, we get aspirin, which is acetyl salicylic acid. Okay. Now, what else do you need to know? You need to complete the practice aspirin sacs on Edmodo. So if you don't have access for some reason on Edmodo, it's always on Dropbox under SAC 3 revision. Okay, so let's start going through some practice questions. Okay, a sample of aspirin was prepared by reacting 2.2 grams of salicylic acid with 4.2 mils of ethanoic anhydride, okay, in a conical flask. Okay, after heating for 20 minutes, the reaction mixture was cooled and white crystals precipitated. The crystals were then collected, dried to constant mass, and weighed. Okay, so we get a mass of our product, and this will be in the liquid state, so our product weighs 2.25 grams. Now the first question, calculate the initial amount in moles of salicylic acid used in this preparation. So this is quite simple. The moles of, oh, that reminds me, before you come into the SAC, you should be quite aware of these molar masses. Even though in this VCAA exam question they've given it to you, you should pretty much commit them to memory, or I might get you to work it out under test conditions, which will be quite time consuming. So let's go back to it. Calculate the initial amount in moles of salicylic acid. So the moles of salicylic acid equals mass over molar mass equals 2.2 over 138, and that should equal 0.0159 mole. Okay, so that's quite a simple one to start off with, and here's the answer here, the VCAA 0.15. Okay, and we don't know where these marks are allocated to because altogether it's 4 marks, so but 7% couldn't even answer this question. Next one, what initial amount in moles of ethanoic anhydride was used? Well, we're only given mils of ethanoic anhydride. We know it's pure, but we can't assume a density of water, i.e. we can't assume 4.2 mil equals 4.2 grams like we can with water. We can't assume that. So we are given the density, which is 1.08 grams per mil. 1.08 grams of ethanoic anhydride equals 1 milliliter. X grams equals 4.2 milliliter. So I'll just do a ratio in that case, and then you get 1.08 over X equals 1 over 4.2, and that should equal 4.536 grams. Now the moles of ethanoic anhydride equals mass over molar mass, 4.536 over 102 equals 0.536 0.0445 mole. Okay. Next question, what is the maximum mass of aspirin that can be theoretically produced from these reagents? We always know that theoretically is through stoic. So basically we have a look and we realize that it's a 1-to-1 ratio, so we have 0.0445 mole of ethanoic anhydride. So we'll just write that in, 0.0445 mole, reacting with 0.0159 mole of salicylic acid. So therefore our limiting, and the one that's going to determine the mass of our product, is salicylic acid. So we basically, the moles of salicylic acid is 0.0159, and that means the theoretical moles of aspirin that should be produced is 0.0159. Okay, so the moles of aspirin, 0.0159 mole. The mass of aspirin equals moles times molar mass, 0.0159 times 180 equals 2.87 grams. Oops. So determine the percentage yield, okay? Because only 2.25 grams was actually produced, it tells you that. So this is actually, to work out the percentage yield, equals actual mass produced divided by theoretical mass produced times 100. Okay, so in other words, 2.25 divided by 2.87 times by 100 equals 78.4%. And if you have a look at all of our answers, we have got them all correct. So we worked out volume times density equals the mass, blah, blah, blah. See, this mass equals VD. I mean, you could use this, or you could just use a ratio, which is what we did. Now, the mass, okay, if unrounded numbers were used, okay, so that's basically keeping it in your calculator because they always accept that. And over here, okay, the use of 2.2 grams rather than 2.50 grams, so basically reading that initial table incorrectly over here with the 2.20 grams of salicylic acid was unexpectedly common. As suggested by the answers, except for this question, some allowance was made for rounding off, while rounding to this was acceptable, to this was not. So basically you can round, but don't shorten your answer too much. This question was generally well done. Okay, so some kids don't use the density provided by the question, probably assuming water, which is 1 gram equals 1 mil, which can't be assumed for other liquids. 2 moles use the same. Okay, not consistent with this requirement. Use the following data. So I think you guys should be fine at that anyway. But let's see, just as a sort of summary. So 32% of the state got all 4 correct. Okay, now let's have a look at the other ones, and they bring back spectroscopy and chromatography, which is excellent. Okay, now I just want you guys to be able to see it. So here we go. Now, describe how the purity of the product could be qualitatively determined using thin layer chromatography. Okay, qualitatively determined means that is there aspirin or not? And purity really talks about is there more than one substance, or just aspirin. Okay, both salicylic acid and aspirin can be detected using UV light, so they really want you to talk about this in the question. Ethyl ethanoate can be used as a solvent. Okay, so you would basically say pop a dot on your chromatography plate, pop a dot of product, place a dot of product in chromatogram and run, in the thin layer and run, full stop. Okay. Okay, and then check for salicylic acid and aspirin under UV light. Okay, and then the second one is if we get 2 spots impure, 1 spot can be pure, can be considered pure. So let's check the answers. So the answers basically only 18% of the state got 2 marks for this question, and they've said basically run a thin layer chromatogram, okay, and check the chromatogram under UV light. If the chromatogram shows 2 or more spots, the sample is impure, okay, and a single spot means that the sample is most likely pure. Okay, so just have a read of this as well. So most students struggled with this question. So basically, okay, so a lot of people said run a chromatogram of both salicylic acid and aspirin, but then couldn't explain how the chromatograms would be interpreted to check for purity. So you could say basically see if the pure sample of aspirin, yours goes to the same point to make sure that it's aspirin, like the same RF value. But you couldn't just say that you're running a pure sample of aspirin without checking if it goes to the same RF value. And also referring to UV light was essential to get your answer, to get the correct answer. Okay, next one. Salicylic acid reacts with aqueous FeCl to form a purple compound. Aspirin does not react with aqueous FeCl3. Describe how the purity of the product could be quantitatively determined using UV visible spectroscopy. So in other words, how much aspirin do we have? We went through a similar one in class. You're going to have to think about, for 3 marks, you're going to have to think about the inclusion of standards, the inclusion of calibration curve, okay, the inclusion of running your sample and checking concentration on the calibration curve, okay. So let's have a look at what gained the 3 marks. Oh, before the standards, selecting optimum non-overlapping wavelength. The reason why we do that is because it's the most sensitive. Okay, so let's have a look at how the state scored for this question. So 9% got all 3 marks. That's why I keep going through this kind of scenario where we're trying to find the concentration of an unknown. So they accepted 3 of the following. That means you don't need to have all 4, but you need to have at least 3 to get the 3 marks. Identify the appropriate wavelength at which a solution of the purple compound absorbs strongly. Okay, why do we want to pick a solution which the compound absorbs strongly? Sorry, a wavelength which it absorbs strongly, because it is most sensitive. So that was step one from my things, which is choosing a suitable wavelength. Make up a set of standards of salicylic acid, okay, slash this, and measure the absorbances to show a calibration curve. Make up a solution of a measured amount of this and measure its absorbance. So your sample, the product is your sample. Use the absorbance to calculate the amount in the compound. Although broad interpretation to the points above was allowed, most students seem to have little knowledge of the stages in quantitative analysis using UV visible spectroscopy. Students are expected to be aware of the need to establish a calibration curve and to relate the absorbance being analyzed to a calibration curve. Many students didn't recognize the significance of the salicylic acid and referred to the solutions of FeCl3. Okay, linking the purity, blah, 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 blah. So I'm sure you guys should do well. It's funny that, it's actually astounding that 57% of the state got 0 for this question overall. Okay, now getting there. So aspirin was derived from salicin, found in a number of plant materials in the body. Salicin is converted into salicylic acid, which is the active ingredient in pain relief. There are 2 steps involved in this process. In the flowchart below, write the type of reaction and draw the structural formula of the intermediate compound and the final compound. Okay, so basically the first step, if you guys remember, is hydrolysis here, where we do get breaking of the ether linkage. Now the ether linkage is going to break down into 2 hydroxyl functional groups. So the product of the first reaction is like so. It's not salicylic acid yet because we have this hydroxyl group at the top, which is a carboxyl group in salicylic acid. And if you wanted to know, the other product, here we go, is here, and it belongs to the monosaccharide biomolecule group. Okay, and OH, here we go. So hydrolysis. And then step 2 is oxidation, and we know what's required, MnO4 negative / H plus, if we want to repeat this in a lab, but we know in the body it's O2 because we have enzymes which can actually perform this. Okay, so then we have, here we go, and we know in hydrolysis it's H2O, and we have something like so, okay, which is salicylic acid. Now, a question, this is a particular question, looking at the digestion of aspirin. So when aspirin reaches the small intestine, a hydrolysis reaction takes place. Okay, what conditions are necessary for this reaction to take place? H2O, and it's actually under a basic environment. Which functional group is involved? Okay, so let's have a look at what aspirin looks like. And we've got here the untouched carboxyl, and we have here OC, here we go. So what functional group is involved and what are the products? So this is the functional group involved, the ester functional group, and the products are salicylic acid. You'll get sick of drawing out salicylic acid when studying for this. And we will get salicylic acid and ethanoic acid. Okay. Here, a student prepared aspirin from 5 grams of salicylic acid, so 5.0 grams of salicylic acid, and the percent, assuming excess of this is the only way you can answer this question, or that it's reacted to the correct amount, and the percentage yield is 54%. Okay, so what mass of aspirin is produced? Okay, let me just grab a piece of paper. So, basically we work out, there are a number of ways you can think about this. You can work out 54% of 5 grams because that is the only mass that's going to react. All of it else will remain unreacted. Okay, so the way we're going to do it is work out the moles of salicylic. So we're going to do it this way. Equals mass over molar mass. 5 over 138 equals 0.036 mole. Now the moles of aspirin, which should be produced, so it's quite theoretical. Theoretical equals 0.036 times the molar mass of aspirin is 180 equals 6.52 grams. Okay, now basically only 54% of that theoretical mass is going to be produced, so times 0.54 equals 3.5 grams. Alternatively, yield equals actual over theoretical, and in this case our actual we don't know, and the theoretical we do know, and the yield, times 100, the yield is 54%, and you solve for x and you get exactly the same answer where the actual equals 3.5 grams. So I hope that helped with your study, and good luck for the SAC on Monday.